Hello guys, this is Vijay and I hope you're doing well. Let's talk about constant volume process. Constant volume process is also known as isometric process or isochoric process. Here, throughout the process, volume remain constant. So, this process is called constant volume process. You can see that the piston is fixed inside the cylinder by some locking device or screw. So, the piston is fixed inside the cylinder, so there is no any movement of piston inside the cylinder. So throughout the process, volume remain constant. So it is called constant volume process. Here you can see that the process on PV diagram 1 to 2 process. So throughout the process 1 to 2, volume remain constant during heat supply or during heat rejection. So V1 equal to V2. It will be represented on PV diagram, pressure versus volume diagram. And during constant volume process, now we derive equation of work done for constant volume process. We have already discussed there are 3 definitions of work done. The first one is theoretical definition. Work done equal to force into displacement, and force means it is an external agency due to that body is occurring a motion and some displacement will be there due to this external agency. It is called work done. The another definition of work done, mathematical definition of work done equal to pressure into change in volume. We have already derived this equation in our previous lecture of basics of thermodynamics. And the area under the curve in PV diagram, it will represent the work done. So there are 3 basic definitions of the work done. The first one is the theoretical definition, force into displacement. The second one is mathematical definition, work done equal to P delta V. Here we are considering delta V equal to area into length. So whenever we derive the equation of work done for constant volume process, we know that the initial volume is V1 and final volume is V2. So here we take the limit V1 and V2 for integration and work done equal to P delta V. But we know that throughout the process volume remain constant. So here V1 equal to V2, there is no any change in volume. So here delta V means dV equal to 0, there is no any change in volume. So work done equal to 0. So in constant volume process there is no any output will be there. Now we derive relationship between pressure, volume and temperature. We know that according to ideal gas equation PV equal to MRT. It is also called general gas equation. So according to ideal gas equation PV equal to MRT, so P1 V1 equal to MRT1 and P2 V2 equal to MRT2. So P1 V1 by T1 equal to P2 V2 by T2. But we know that for constant volume process, throughout the process volume remain constant. So here V1 equal to V2. So from left hand side and right hand side V1 equal to V2, so it is cancel out. Finally the relationship between pressure and temperature equal to P1 by T1 equal to P2 by T2. Now we derive equation of change in internal energy. We know that according to first law of thermodynamics, delta Q equal to delta U plus delta W, where delta Q is heat transfer, delta U means internal energy and delta W means work done. But in constant volume process work done is 0. We have already proved in our derivation. So du equal to mcv delta T. We know that internal energy, it's a function of temperature. So internal energy equal to mcv delta T. But in constant volume process work done is 0. So delta W equal to 0. Put this value in equation of first law of thermodynamics. Delta Q equal to delta U plus By first law of thermodynamics, delta Q equal to delta U plus delta W. So we have already proved that for constant volume process work done is 0. So the equation of internal energy and the equation of the heat transfer both are same. And we know that the equation of internal energy is mCv delta T. So the equation of heat transfer and equation of internal energy is mCv delta T. Now we derive the equation for change in enthalpy. We know that enthalpy, it's a sum of internal energy plus the product of pressure and volume. So for process 1 to 2, here we are considering at state 1 enthalpy equation H1 equal to U1 plus P1 V1, and for state 2 H2 equal to U2 plus P2 V2. State means we have already discussed in our previous lecture of basics of thermodynamics. State means it will be described by minimum 2 properties. So here one property is remain constant throughout the process, volume remain constant. So here we are considering 2 remaining properties, pressure and temperature. So H1 equal to U1 plus P1 V1 at state 1, and for state 2 H2 equal to U2 plus P2 V2. Now abstract H1 from H2. So delta H equal to H2 minus H1 equal to change in enthalpy. But we know that H equal to U plus PV. Put the value of H2 and H1 in equation of delta H. Put the value of H1 and H2 in delta H equation. So delta H equal to H2 minus H1, where H2 equal to U2 plus P2 V2 and H1 equal to U1 plus P1 V1. Put this value in this equation. So finally we derive the equation delta H equal to U2 minus U1 plus P2 V2 minus P1 V1. But we know that change in internal energy equal to mCv delta T. Internal energy, it's a function of temperature. So internal energy equal to mCv delta T. Put the value of equation in terms of temperature, and we know that T equal to mRT by ideal gas equation. So put the value of P2 V2 equal to mRT2 and P1 V1 equal to mRT1. So we simplified the equation delta H equal to mCv T2 minus T1 plus mR T2 minus T1. But we know that R equal to Cp minus Cv, where R is gas characteristic constant, and it is a difference of 2 specific heat. So put the value of R equal to Cp minus Cv in this equation. So finally equation of enthalpy equal to mCp delta